Problem number 29 states the following. Use a hydrogen fusion to supply the energy is a dream that may be realized in the next century. Fusion would be relatively clean and almost limitless, as seen in Table 1. To illustrate this, calculate how many years the present energy needs of the world would be supplied by 1/1,000,000th of the ocean's hydrogen fusion energy. And then B is, how does this time compare with historically significant events such as the duration of stable economic systems? Well, first of all, the 1/1,000,000th, if you take the energy from hydrogen fusion and take 1/1,000,000th of that and compare that to the world's economic energy, not economic, but energy needs, you'd end up with 10 to the 34th divided by, or multiplied by 10 to the minus 6, divided by 10 to the 20th, 4 times 10 to the 20th, and you'd end up with essentially 2.5 times 10 to the 7th years. And obviously that amount of time is extremely long. So the energy from fusion is known to be a real potential boon if we could ever tap into it. The Crab Nebula, this is number 30. The Crab Nebula is a remnant of a supernova which occurred about 1,000 years ago. From data in the table 7.3, calculate the approximate factor by which the power output of this astronomical object has declined since its explosion. Okay, let's take a look at that. Basically, it's the original P, or the current P divided by the original P. The current P is 10 to the 28th. Based on the table, and the original was 5 times 10 to the 37th, and so it's 2 times 10 to the minus 10 less than the original power output. Number 32 talks about the amount of output from one person is approximately 100 watts, which is 100 joules per second. So how many people would it take to produce 4,000 watts? We get from one person, we get 100 watts. So that's going to take 40 people to generate 4,000 watts of power. The second part of this question says that in order to power a situation, it takes 8 times 10 to the 8th watts, and if you can produce 100 per person, how many people would it take to produce this? And essentially it takes 8 million people, or 8 times 10 to the 6th people, to produce this kind of energy level. Number 38 states the following. A, how long will it take an 850 kilogram car with a useful power output of 40 horsepower, 1 horsepower is equal to 746 watts, to reach the speed of 15 meters per second, neglecting friction? Well, we know that power is equal to work divided by time. So work is equal to power times time, and time is equal to work divided by power, which in this case is going to be equal to 1/2 mv squared divided by the power output, which is 40 horsepower times 746 watts per per horsepower. So if we put this number in, we get 1/2 times 850 times 15 squared divided by 40 times 746, and that's going to equal 3.2 seconds. The second part of this says that we're now going to go up a small grade that's 3 meters in height. So how long would it take to do that? And basically we take the same equation and we just add, so we have the kinetic energy, but now we have to add the potential energy of going up 3 meters using the same power output. So we sacrifice, or it takes a longer period of time because we've added this second factor. If you do the calculation here, you now get 4.04 seconds. Number 39 asks a similar question regarding power, except now we're going to ask for the power output if we know the time, which in this case is 12 seconds. So work that this system is doing is going to equal the change in kinetic energy for the system plus the change in potential energy. And if there were any other factors such as heat or friction or other things, but it doesn't mention that, so this is going to be 1/2 mv squared plus mgh. So that's the work part. So basically the power is going to equal 1/T times this same set of factors. So if we put in 1/12, because it's 12 seconds, the mass times the velocity squared plus, now the mass of the elevator is the total mass, but the mass that's being lifted is only the amount that's above and beyond the counterweight, which is why these two masses are different, and it mentions that in the problem. And we raise this 35 meters. So the change in velocity for the elevator has to be for the total mass, but the change in height is for the non-counterweighted mass. And that's why these two numbers are different. You do this calculation and you get a power output of 7.81 times 10 to the 4th watts. And then it says that a kilowatt hour of power costs 9 cents. So how much is this going to cost? So this is actually 78.1 kilowatts. And we multiply this by 9 cents per kilowatt hour. And then multiply that by 12/60, because 12 seconds. And we end up with $1.41 to lift that up.